Hey everyone, welcome to Chapter 17, Section 1. Alright, Chapter 17, Section 1 is all about something called the common ion effect. So here's kind of like a essential question for this section, something to kind of keep your head wrapped around. It is this: how does the addition of a salt to an acid change the ionization of that acid? So now that you've got kind of a firm grasp on equilibrium, you kind of understand that every acid has a conjugate base, and vice versa, every base has a conjugate acid. So if I were to stick a ionic compound, say like sodium acetate, into acetic acid, how would that affect the overall equilibrium? Will it change?
The common ion effect is very, very simple to explain, but it's hard to actually do the math, and so I really wanted to concentrate on that right now. So I gave you a quick sample problem here. It says, calculate the fluoride ion concentration and a pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. So HCl versus HF. Which one of those is a strong acid and which one of those is a weak acid? I hope by now you've got that thing memorized in Chapter 4. I really, really need you guys to commit that to memory. All of the strong acids and the weak acids, and strong bases and weak bases. Alright, so HF is a weak acid. HCl is a strong acid. HF will only partially ionize because it's a weak acid. So that's the one that we're going to have to concentrate on. You should look up the Ka value for HF. The Ka value for your HCl is going to be really high, like, in the hundreds or whatever, so you know it's going to mostly lie on the product side in the ions. So we're worried mostly about this HF. So you'd have to look up the value for Ka for HF, and we did. And for this acid, your Ka value, our expression, would be the products, your hydrogen ion, your fluoride ion, over your reactants, the HF, the acid. Alright, so let's keep going. We're concentrating on this whole, pH thing. We're trying to figure out how many hydrogen ions basically we have in order to solve for pH. Not worried about HCl, we're only worried about HF. So here we go. Okay, so since HCl is a strong acid, notice in your ice table that you're actually going to have to represent the initial concentration of your H plus with 0.10. That's what was given in the problem. Your HF is 0.20, which was also, again, given in the problem. Your ice table will be set up just as normal with the X's. So you're going to lose a certain amount of HF and you're going to gain a certain amount of hydrogen ion and fluorine ion. But here's the tricky part. When can you ignore the X? Okay, this is really hard to remember. It says if the value of X is more than 5% of the initial concentration of your acid, then you will need to use the quadratic equation or successive approximations to solve for the problem.
So we're going to go ahead and just solve, assuming down here at the equilibrium that anything that is being subtracted by X is negligible. So you see how I reduced the Ka value over here to just 0.10x on the top and 0.20 on the bottom? So go ahead and solve for your x, and then once you do, you're going to compare this x value to the original concentration of your acid. And we just want to make sure that it is less than 5%. Okay, so when I solve for x, I get 1.4 times 10 to the negative 3. So what I'm going to do now is I'm going to take that value and I'm going to put the original concentration of 0.20 on the bottom and then times it by 100. And this will tell me what percent that value is of the original concentration. And I get 0.7%. So we can assume that X was so small that it could actually be ignored. Bravo! So we solve for X.
So therefore your fluorine ion is also equal to X, which is equal to 1.4 times 10 to the negative 3. Your total concentration of your hydronium ion is 0.10 plus X, which is equal to 0.1. And that's really easy. That means that your pH is 1. Okay, so we solve for the fluorine ion concentration, we solve for the hydrogen ion concentration, and then we solve for pH. Okay? Here's a sample exercise 17.1. This is in your textbook. The question is, it says we are, oh, I think I have to, there we go. It says, what is the pH of a solution made by adding 0.3 mole of acetic acid and 0.3 mole of sodium acetate to enough water to make a 1 liter solution? So you need to look at the names here and decide what your common ion is. It says we're asked to determine the pH of a solution of a weak electrolyte, that's called acetic acid, and a strong electrolyte, sodium acetate. And they share a common ion, the acetate ion. So when you plan these things, it says in any problem in which we must determine the pH of a solution containing a mixture of solutes, it's helpful to proceed by a series of logical steps. So obviously we want to know what these steps are, and we're going to make sure that you put these down in your guided notes. Number 1. Consider which solutes are strong electrolytes and which are weak. In other words, which one will fully ionize and fully dissolve, and which one will not do that. And then it says identify the major species in the solution. So basically which ion is in majority, which ion is minority. Alright, number 2. Identify the important equilibrium that is the source of your H+, and therefore will determine your pH. So remember how in the previous chapter, chapter 17, we learned that certain ions, when they're weak in solution, can change the pH because they hydrolyze with water. And that is what we're looking for. We're looking for weak ions that will alter the pH of your solution. Number 3. Tabulate the concentrations of ions involved in the equilibrium, and then using an ice table typically. And number 4. Use the equilibrium constant expression, your Ka, to calculate your concentration H and therefore your pH. Alright, so 4 steps. You've got to have them memorized. This is the common ion effect. Here we go. It says, first, because CH3COOH is a weak electrolyte, that's a weak acid, and the sodium acetate is a strong electrolyte, it means that the major species in the solution are the CH3COOH, your weak acid, Na, which is neither acidic nor basic, right, which doesn't really matter, and then your CH3COO, your acetate ion, which is your conjugate base of CH3COOH. So that's the first step. Second, H+, and therefore your pH, are controlled by the dissociation equilibrium of your acetic acid. And it says we have written the equilibrium using H+ rather than H3O+, but both representations of the hydrolyzed or hydrated hydrogen ion are equally valid. They just did that in the book, so I wanted to make a note here too. Alright, so it says H+ concentration, and therefore your pH is controlled by the dissociation equilibrium of your CH3COOH. Okay, so here's your ice table. Now, you need to be careful. You have the initial concentration of your acetic acid right here, but you also have the initial concentration of your acetate ion, because that came from your sodium acetate. Sodium acetate will fully ionize, right? Because it's a strong electrolyte. So your ice table should start with an initial concentration on your acetate ion too. Okay? So that's where these initial concentrations came from. Obviously this guy's going to ionize, so minus X plus X plus X. Here's your equilibrium amounts here. Okay? Alright, so obviously we're going to need a Ka value for this acetate ion, so we're going to obviously need to look this guy up. It says, third, we tabulated the initial and equilibrium concentrations as we did in the previous example in chapter 15 and 16. It says the equilibrium concentration of your acetate ion is the initial concentration due to that sodium acetate, plus any change that you get from the acetate, or the acetic acid. It says now we just use that equilibrium concentration, so you'd have to look that up for your acetic acid. It's 1.8 times 10 to the negative 5. Notice that they put the products on the top, the reactants on the bottom, so there's our Ka equilibrium expression. And then it says the dissociation constant for CH3COOH at 25 is from Appendix D. So that's something that they'll have to give you on the AP exam. And of course there's not going to be any kind of equilibrium expression for the sodium acetate. That's because it's a really strong ion. You don't have to worry about that. Alright, so now we got to just substitute our equilibrium stuff. So we got X for H, 0.3 plus X for your acetate, and then 0.3 minus X for your acetic acid. Alright, let's keep going. So here's the hard part. Your Ka is really small, right? Your Ka value, again, is 1.8 times 10 to the negative 5. How does that compare to your 0.30 molar? It says because Ka is small, we assume that X is small compared to the original concentrations of acetic acid and acetate. Thus, we can ignore very small x relative to the 0.3 m. So I wanted to show you one more time how that goes. On your calculator, it's very simple. You're going to take your Ka value, 1.8 e negative 5, divide that by your 0.30, and now times that by 100 to change it into a percent. You literally have a very small fraction of a percentage. So you are justified in ignoring those x's for the for these concentrations right here. We threw minus x out for each of these. Okay. Alright, so that makes it much easier. So your x is really easy to solve for. X is 1.8 times 10 to the negative 5. Hey, look at that. It's pretty much your Ka value, right? That should make sense. And it says, finally, we calculate the pH from your equilibrium concentration of H+, pretty easy, and you get 4.74. So in other words, what this meant is that the addition of the sodium acetate didn't really affect the concentration of the H+ ion. And here's your comment. It says in section 16.6, we calculated that 0.3 molar of acetic acid has a pH of 2.64, corresponding to your H+, which is 2.3 times 10 to the negative 3. It says, thus, the addition of sodium acetate has substantially decreased your hydrogen ion concentration, as we would expect from the Le Chatelier principle. So, here's a recap. Here is your acetic acid. I'm not going to write the whole anion part here, okay? Alright, so if you add more acetate ion here, how do you expect the equilibrium to shift? Okay, so if I added more acetate ion to this equilibrium, how would this thing shift? According to Le Chatelier, if you add more of the products, it's going to shift towards the reactants. And if it shifts towards the reactants, look at what's happening to your H+ concentration. Right? If you are removing some of your products to get rid of this, that means your hydrogen ion concentration is going to drop. It's going to lower with the addition of this. Okay? So this should pretty much make sense. Okay. Going on to example 17.2. Alright, question. Calculate the fluoride ion concentration and pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. It says we can use the same 4 steps that we first used in example 17.1. So it says because HF is a weak acid and HCl is a strong acid, the major species are HF, H+, and Cl-. The chlorine ion, which is a conjugate base of a really strong acid, is just a spectator ion, so you should ignore the chlorine. Okay? So it sounds like the HF ion is kind of our main problem here. It says the problem mass for fluorine concentration, which is formed by the ionization, which is formed by the ionization of HF. Thus, the important equilibrium is this guy, your HF forming H+ and F-. Alright? So you always want to write the hydrogen ion in your product, just in case you were wondering, because we're trying to find the pH. We want the hydrogen ion to be in the product, okay? Let's keep going. The common ion in this problem is the hydrogen, or hydronium, Okay, that just was random. Alright, it says the common ion in this problem is the hydrogen or hydronium ion. It says now we can tabulate the initial and equilibrium concentrations for each. Alright, so coming back over here, you've got the HF concentration right there. You have your initial hydrogen ion concentration because what they started you off with is a strong acid. Go back up here. You have HCl, strong acid, HF, weak acid. So we're assuming that this whole thing will ionize. So you should have an initial concentration on your H plus as 0.1. Do your traditional ice table. Here are your pluses and your minuses. You're going to try to find the Ka value for your HF. 6.8 times 10 to the negative 4. Compare this with your initial concentration of your HF. 0.2 versus 6.8 times 10 to the negative 4. Pretty sure we're safe with ignoring the plus x and the minus x, okay? So go ahead and throw those out. Solve for your x. It's 1.4 times 10 to the negative 3. So we know that's your fluorine ion concentration, but look at your ice table. For your H plus, you're going to need to do some addition here. Alright, it says thus F concentration is substantially smaller than it would be in a 0.2 molar of HF with no added HCl. The common ion H plus suppresses the ionization of HF. Therefore, the concentration of H plus is pretty simple. You're going to do 0.1 plus x, which is really, really small, and it's basically just equal to 0.1. And so your pH will be about 1. Look back at the value of x. It was 1.4 times 10 to the negative 3. What is 0.1 plus 0.0014? 0014. It's basically, to 2 sig figs, it's still, or even 3 really, it's still 0.101 technically. So very, very slightly changed. So it says, notice that for all practical purposes, H plus is due entirely to your HCl in this particular case. The HF makes a negligible contribution to your H plus concentration. So that was a really good example there. Alright guys, we're done on this podcast. When you guys come in, obviously, I know this is a tough subject, the common ion. Your ice tables look totally different. So I'm going to give you a minute to simmer on this. If you want to start on your bookwork or finish the bookwork from the previous class, that would be a really good idea. Always email me questions, alright? So finish your bookwork from chapter 16 if you haven't done so already, and we'll do chapter 17 bookwork in class next time, alright? Adios!